Welcome to another tutorial. Here I show how to model a 3-jaw chuck in Solidworks for 3D printing. The parts are printed from PLA+, ABS, and PETG. This is what the final 3D printed assembly looks like. Here is the exploded view in Solidworks. As you can see, there are 3 pinion gears that turn a bevel gear. The bevel gear is connected to the scroll plate, which has a spiral-shaped helical sweep. This sweep moves the jaws simultaneously inwards and outwards. The names of the parts are shown here. Pinion gears in yellow, chuck housing front and back in gray, jaws in blue, driven bevel gear in green, and scroll part in light blue. Pinion gears turn the bevel gear, which has a scroll plate on other side. Here is the completed assembly, and we are viewing it from the scroll plate side with the chuck housing front in transparent state. The pinion gear turns the scroll plate, which causes the jaw to translate towards the center of the chuck and away from the center of the chuck depending on the direction of rotation for the pinion gear. We start with modeling the scroll plate. This part threads onto the bevel gear. Here is the basic revolve profile. Start a sketch on the right plane with a center line and add the dimensions to the geometry accordingly. Now we need to add appropriate size threads to connect the scroll plate to the bevel gear. I selected M55 by 4 threads. Now in equations, add the external diameter, pitch, thread height, and thread radius. I have a video on my channel showing how to cut external and internal threads in Solidworks. Feel free to check that video out if you like. Next, set the dimension to external major diameter and cut the external thread as shown using the swept cut command. Where the profile is the thread and path is a helical curve. Before cutting the thread, we need to add a small chamfer to the face. Add a helical spiral where the diameter is the external major diameter and the pitch is equal to the pitch of the thread, or 4 mm per thread. Before moving forward, it is good to create an axis that goes through the part. Next, create the thread profile on the right plane. The thread profile has a 60-degree angle, and the dimensions for external major diameter, thread radius, and pitch come from the equations that we added previously. Constrain the line to be horizontal and draw a vertical line between the bottom of the thread and middle of the thread. Constrain this vertical line to intersect at the midpoint. Create a 3-point arc connecting the horizontal line to angled line. Mirror this arc about the center line of the thread and set a tangent constraint between the arc and the lines. Create a fillet at the bottom of the thread and set the radius to thread radius from variable defined in equations. final step for the scroll plate part is to add the scroll. The scroll is a sweep where the profile is rectangular and the path is a spiral. First, create the spiral by setting the pitch and number of revolutions. Then create a sketch of a rectangle on the right plane to be the profile of the sweep. Draft the end faces of the scroll plate spiral using the draft command with a 45-degree angle towards the face of the part. Set the face to draft as the small face and the neutral plane as the large diameter face. Change the color of the part to green so we can see it in the assembly. The next part to create is the bevel gear, which will thread onto the scroll plate part created previously. I have a tutorial on my channel on how to create a template for bevel gears. Feel free to check out that tutorial. The bevel gear that is selected for this project has a module of 3 and 15 teeth for the pinion gear and 45 teeth for the driven bevel gear. We start by modifying the revolve of the bevel gear by trimming these lines and decreasing the size of the bevel gear. Looks like there is an error here which may have occurred due to changing the revolve sketch. The error is due to deleting the axis of rotation of a single tooth cut for the bevel gear. Create a new axis by selecting the right and top planes, and then set it as the axis of rotation to resolve the error. Next, we add equations for pitch, internal minor diameter using the minimum dimension, thread height, and thread radius. The process is similar to the one shown previously for the external thread. Again, as a reminder, I have a full video on how to cut internal and external threads in Solidworks on my channel, so feel free to check it out if you need to. Now that we have defined a dimension for the internal minor diameter, we can use it to modify our sketch. We set the internal diameter of the bevel gear to this dimension so that we can cut the internal threads of AM55 by 4 thread. To create the internal threads, we first have to create a small chamfer. Now, we create the thread profile, which is going to be the profile for the swept cut feature that will be created later. It is good to create a section view with the right plane to help us see what we are doing. To create the thread profile, we start with a sketch on the right plane. Draw a triangle. Draw a center line over the axis of the part and set this line to construction. Draw a vertical line from the top of the thread to the center and constrain it by making it vertical and coincident to the midpoint of the bottom line. Set the length of the bottom line of the triangle to the pitch. Set the angle between the two lines to 60 degrees. Set the diametrical dimension of the bottom line of the thread profile to the one defined in equations for internal thread minor diameter. Now create a 3-point arc for the bottom corners of the triangle. Create a tangent constraint between the arc and the angled line. Trim the previous line and mirror this arc using the profile centerline as the mirror line. Trim the extra line that is on the other side as well. Then, set a coincident constraint between the end of the three-point arc and the bottom leg of the triangle. It will automatically get set on the other side since this arc is mirrored. I will need to delete the dimension for the length of the bottom leg and redefine it because Solidworks is not able to find a solution as the sketch is defined now. I remove 0.005 mm from the pitch so that Solidworks does not give an error while performing the swept cut. The next step to creating the thread profile is set another tangential constraint between the arc and the bottom line of the triangle. The radius of the arc is set to the thread radius defined in the equations previously. The final step for creating the thread profile is to create a fillet at the top corner of the triangle. The radius for this fillet is also set to the thread radius variable defined in equations. It looks like I did not define the helix, which is what I like to do before creating the thread profile. No problem, we can just change the end of part by dragging the line above the sketch that we created previously. Now to create the helix we need to create a sketch that includes just a circle. The diameter of this circle is set to the internal minor diameter defined in equations previously. To create the helix we define a height and pitch. The height just needs to be large enough to go through the part along the z-axis and the pitch is equal to the thread pitch. The final step for completing this part is to create a swept cut feature. The swept cut feature requires two inputs. A profile, which is the thread profile, and a path, which is the helix. You do need to make sure that the helix starts on the same plane of the thread profile sketch or else you will get an error. We can now begin creating an assembly using the two parts that we have created. The two parts are the scroll plate and the bevel gear. Let's start by brining in the bevel gear. Let's start by defining an axis for the assembly using the top and right planes of the assembly. Then, create a coincident constraint between the bevel gear axis and this assembly axis. Next, set the right plane of the assembly coincident to the right plane of the bevel gear. And finally, set the front plane of the bevel gear coincident to the front plane of the assembly. Now that the bevel gear is fully constrained, we can bring in the next part, which is the scroll plate. To constrain the scroll plate, we start by creating a coincident mate between the faces. Then, we align the axes to one another. Finally, to fully define the scroll plate, we set the right planes of both parts to coincident. I noticed that I set the color of both of these parts to green, so I will go back to the scroll plate and set it to a bluish color. The next part to create is the pinion gear that will drive the bevel gear. The pinion gear is selected using the same module, number of teeth for the pinion, and number of teeth for the bevel gear. Those values are 3, 15, and 45 respectively. The only change we will make to the pinion gear is to add a hexagonal-shaped extruded cut. This hexagonal-shaped extruded cut will fit a 13 mm Allen key. The depth of the cut is 20 mm. We change the color of the pinion gear to yellow so that it can be easily viewed in the assembly. Again, I will remind the viewer that there is a video on my channel showing how to model bevel gears. It is a pretty involved process that requires its own dedicated video. Feel free to check that video out from my channel as well. Now let's add the pinion gear to the existing assembly. We start by creating mates between the pinion gear and the assembly. We need to use the pitch lines to create the assembly mates, so I will select the sketches from the bevel gear and the pinion gear that contain the pitch lines and show them in the assembly. Pitch lines are lines of action between two mating gears. It looks like I don't have an axis for the pinion gear. So, let's open the pinion gear and create an axis using the top and right planes. You can use the cylindrical face instead of an axis for a concentric mate in assembly, but I prefer to use an axis because I know it will always be available and it is more intuitive. We start constraining the pinion gear by mating the right plane of the gear with the right plane of the assembly. Then we mate the pitch line of the pinion gear to the pitch of the bevel gear. These sketches need to be shown in the part in order to select them in assembly. The final constraint is to set the line that defines the back or end of the gear's coincident. Once again, this line is available in the sketch used to create the gear, so it must be set as shown. Now we can hide the sketches for the pinion gear and bevel gear because their lines are no longer needed. Further, they are annoying to see in assembly. Now, we can have a bit of fun by giving our assembly a satisfying twirl to see how it looks from various angles. Next, we need to create a housing for the chuck. The housing is split into two parts that are bolted together using M6 size bolts. The purpose of the chuck housing is to hold the bevel gear and the pinion gears in place so that turning the pinion gear will cause the bevel gear to rotate. I aptly named the two sides of the chuck housing as chuck housing front and chuck housing back. We will start with the chuck housing front. To create this part, we begin with a sketch that will be revolved. Again, I like to create an axis between the top and right planes as it is useful for creating revolves, mating, circular patterns, etc. The sketch to be revolved needs a center line that is coincident with the axis created previously. This center line will be used to create the diametrical dimensions. The dimensions along the z-axis are mainly constrained by minimum wall thicknesses and have to be long enough to hold the scroll plate and bevel gear. The hole in the part reduces the amount of filament and weight of the part. The large outer diameter is set to 160 millimeters. The smaller outer diameter is set to 45 millimeters so that the scroll plate and bevel gear fit snugly to it. The inner diameter is set to 32.5 millimeters and the rest of the dimensions are set based on what looks appropriate. Going back to the sketch, we just need to set a collinear constraint between these two lines. I also set the inner diameter to 140 millimeters to clear the outer diameter of the scroll plate and bevel gear. The next step is to cut the paths for the jaws. There are 3 jaws, so a circular pattern of 3 jaw paths will be created. The jaw path is cut from the larger outer diameter up to the smaller outer diameter, as we will see in the coming steps. I first create a sketch on the XY plane with 1 jaw path and then create a circular pattern of 3 paths around the center. This will help us visualize what is an appropriate size for the jaw paths. I want to make sure that the paths are large enough to hold a reasonable size jaw, but not too large to the point where I have no material left in the chuck housing front part being modeled here. Now you can get arc dimension by clicking on the 2 arc endpoints. I set this dimension to 1 millimeter to ensure that I maximize the size of the jaw paths and that I have some wall material after I create the cut. Next step is to create a plane which starts at the outer diameter of the part. This plane will be the sketch plane for the jaw path cut. Now we create the sketch for the jaw path. Start by drawing a profile for what the jaw will look like. Place a center line that is coincident with the axis in the middle of the profile to be used for mirroring and dimensioning. The dimensions are basically designed to be big enough to allow for translation of a 3D printed jaw. The jaw is the smallest part of this whole assembly. Here I changed the sketch plane to the outer plane. I was accidentally sketching on the incorrect plane. You can right-click on a sketch and change the sketch plane from the pop-up menu. Set a pierce constraint between the corner of the jaw cut profile and the sketch that was previously created on the XY plane. Grab the bottom surface of the face where the scroll plate and bevel gear will sit and use the Convert Edges command to create a line on the sketch plane. Convert this line to construction. Use the cut feature to extruded cut this profile created. Start from the sketch plane for the cut. Under Directions, select up to Surface and select the outer cylindrical face shown. The next step for creating this part is to cut a semicircular shape. This shape will be for the pinion gears. The pinion gears and the jaws will be in the same planes as one another, and there will be 3 of each. Set a coincident constraint for the circle and set the diameter to 40 millimeters. Make sure that the cut clears the part in both directions. Now we need to cut a little material to clear the large part of the pinion gear. Remember that bevel gears do not maintain the same diameter and that they are larger towards the outer portion of the gear. Start by creating a sketch on the face of the housing. Draw a center line that is coincident with the axis of the part and draw a rectangular shape that will be used for the revolved cut feature. The final step for creating this part is to create internal threads for an M6 size bolt. This process is similar to the one shown before where we define variables in equations. Then create a profile and helix. After that, use the swept cut tool to create the threads. The difference for this thread profile is that we need to create a plane at 60 degrees to act as the sketch plane for the profile. Now let's place the chuck housing front part into the assembly. First, we constrain the axis of the chuck housing front to the assembly axis. Then, constrain the bottom face of the scroll plate to the face of the chuck housing front. This assembly shows why I printed the scroll part and the bevel gear as two separate parts, whereas you would likely find it as one part if it were made out of steel. When it is two parts, one can print both the scroll plate profile and the bevel gears in the up direction. This ensures an accurate and smooth finish, otherwise I would have to remove support material, which does not give accurate dimensional results depending on the level of patience that I have when removing the supports. Finally, we constrain the pinion gear to the semicircular cutout in the chuck housing front. Showing a section view of the assembly helps us visualize that everything is placed correctly. Now we see that there is some interference between the fillet of the chuck housing front and the helical spiral profile of the scroll plate. This is resolved by decreasing the number of revolutions for the helical spiral profile. The next part we need to create for the assembly is the chuck housing back. This part is very similar to the chuck housing front. We start with creating a sketch that is going to get revolved on the right plane. We need a center line for dimensioning and revolving purposes. Now create a plane that is parallel and tangent to the top plane. This will be the sketch plane for the semicircular cutout. This will be lined up with the other semicircular cutout on the chuck housing front part. Together, they will hold the pinion gear in place. Create a sketch on this plane and draw a circle that has a diameter of 40 millimeters. Create an extruded cut through the entire face of the cylinder from the outer diameter to the inner diameter. Now, we need to create a small extra cutout, just like with the chuck housing front, where we needed to remove a little extra material to accommodate the larger portion of the pinion gear. Start by creating a sketch on the face of the cylinder. Draw a center line to dimension from and draw a rectangle. We use the same exact dimensions as the chuck housing front for the sake of consistency. Then create a revolved cut from the rectangle, and the profile that holds the pinion gear is now complete. We also need to create an axis for this part. Then create a circular pattern around this axis. Now, we also need to create a through hole for the size M5 screw that will hold the chuck housing front and chuck housing back parts together. These through holes will be located at angles between the revolved cuts for the pinion gears. Since we are going to circular pattern these three holes, let's bring the bottom of part line up before the circular pattern in the Solidworks feature tree. Draw a construction line that falls between any of the two of the revolved cuts. Dimension this line to be 60 degrees. Draw a circle that is 6 millimeters in diameter for the M5 screw. Create a coincident constraint between the center of the circle and midpoint of the construction line drawn between the inner and outer diameters of the chuck housing back. Now, we need to remove some material where the through holes. This will allow us to use the M6 screws that we have, which are 30 millimeters long. To create this cut, we need to create a few features before that. The first feature is an axis for the through hole that we created previously. Then a plane that contains both the axis of the through hole and the axis of the part. Next, we create a plane that is perpendicular to the previously created plane. Finally, create a plane that is going to be the sketch plane for the rectangular profile cut. Looking back at it, I see that there could have been an easier way to create this plane, but this is the method that occurred to me while I was modeling this part. Now create a sketch on this plane. The sketch is a rectangle to be used as a cut from the outer diameter to the inner diameter of the chuck housing front. Let's leave about 10 millimeters of wall after this cut. Now, include this rectangular cut in our circular pattern to finish the part. Now, the final step is to include the chuck housing back into the assembly. The constraints for the chuck housing back are similar to the constraints of the chuck housing front. Namely, they are an axis constraint between the center axis of the part and the center axis of the assembly. We also need a coincident constraint between the two mating faces of the chuck housing front and the chuck housing back. Finally, we need to constrain the axis of the cutout to the axis of the pinion gear. After placing this part in the assembly, we realize that the rectangular cut is placed incorrectly and should be removed from the other side. This is an easy fix. All we need to do is edit the sketch of the cutout. Solidworks automatically goes into edit mode of a part when we select edit sketch of a part in an assembly. Isn't Solidworks just terrific? Edit this sketch to create the cut on the proper side by trimming the existing coincident line and removing the coincident constraints between the points and the line. Create the 10 mm dimension as before. Finally, let's create a circular pattern in assembly mode of the pinion gear. The next parts to create are the jaws. The jaws will be created using Solidworks Combine feature with the existing scroll plate. So we will open the scroll plate and save it as a new part aptly named scroll plate for cutting jaw. The bottom of the jaws mate with the helical spiral profile of the scroll plate, therefore the bottom of the jaws will have the negative profile of what is on the scroll plate. To create this profile, we start by deleting the drafts because they are no longer needed. We extend the spiral of the helical spiral sweep outward to extend past the outer diameter of the scroll plate. This is done by defining another helical spiral that starts at the same location of the original helical spiral but goes in the opposite direction. Select Helix from the Reference Geometry drop-down menu. We are now prompted to create a sketch with a circle. This circle has the same diameter as the diameter of the scroll plate. Reverse the direction of the helical sweep and use the same value for pitch as before. We do not need the same number of revolutions as before, we only need a few to be able to cut the jaws from the bottom side as will be shown shortly. The next step is to create a plane for each jaw. By convention, we set jaw 1 to be perpendicular to the right plane. So, I renamed this plane to jaw 1 to help us identify it later. Here, I created an assembly composed of the scroll plate for cutting jaw part and the chuck housing front part. I did not show the steps for creating this assembly, but it is a few simple mates that you should be able to figure out by following along other assembly creations. Now, enter edit mode for the scroll plate for cutting jaw part and create a sketch on the jaw 1 plane created previously. Use the Convert Edges tool and select the cutaway path profile in the chuck housing front part to bring these lines into the sketch. Now, exit the sketch and end the edit part mode in assembly. Open the scroll plate for cutting jaw part by itself because we have what we need from assembly mode and can concentrate on creating the jaw 1 profile. Select and convert the lines of the cutaway for the jaw profile in the chuck housing front part to construction lines. We need to remember that the jaw slides through this cutaway profile and thus needs to be a little bit smaller. How much smaller? Well, this really depends on your printing capabilities and how tight of tolerances you can obtain for bridged parts. For me, I am using 1/2 millimeter. Draw a center line in the middle of the jaw to use as a mirror line. Select the lines and mirror about this center line to finish the sketch. Now, extrude the sketch to create the first jaw, or what we are referring to as jaw 1. We create jaws 2 and 3 the same way. But, First, we need to create new sketch planes that are 120 degrees apart. Jaws 1, 2, and 3 are the same, but the only difference is that they have a differing cut profile at the bottom, so that they are all exactly the same distance from the center of the chuck at the same time. Here, I go into assembly mode in order to define the planes for the other jaws to make sure that they are correctly placed. I then rename the plane for Jaw 2 as Jaw 2 plane. Next, we create a sketch on this plane much like we did for Jaw 1. Select the Convert Entities feature and select the lines that define the cut profile for Jaw 2 in the chuck housing front part. Once again, offset the entities inward because the Jaw 2 will be slightly smaller than the Jaw 2 cut profile from the chuck housing front part. Use an offset of 0.5 millimeter. Convert the lines that were converted from edges to construction lines. Draw a line in the middle of the part and use the mirror command. We will now configure this part in 3 derived parts, which are Jaw 1, Jaw 2, and Jaw 3. In order to configure a part in Solidworks, just right-click on the feature that you want to be varied for each configuration and select Configure Feature. Add 3 rows to the Configure Feature table and name each row Jaw 1, Jaw 2, and Jaw 3. Solidworks will automatically create different configuration for this part. Each configuration will have the remaining jaws suppressed. For example, for the Jaw 1 configuration, Jaws 2 and 3 are suppressed and so forth. Now let's check if the configurations are working properly by selecting the derived parts Jaw 1, Jaw 2, and Jaw 3. The next step is to use the combine feature with the subtract option. I note that the combine feature is dim and not available. This feature is only available if there is more than one body available. I need to go back to the extrude feature and uncheck merge result. That will result in two bodies for this part, and now the combine feature is no longer dim and available. I will use the subtract option for the combine feature where the main body is the jaw and the bodies to combine is the scroll plate. We note that the jaw is cut with the proper profile using the scroll plate from the bottom side as required. Now, I have to repeat the same steps for the other two configurations. First, uncheck the merge result tick box in extrusion feature and combine the extrusion with the scroll plate. Once again, we inspect all three configurations to make sure that we have the desired result. And of course, the mandatory Solidworks twirling of the part. Now there is one important step that needs to be done before the combine feature. This step is to slightly increase the size of the helical spiral profile of the scroll plate part. This profile must be increased or the profile on the jaws will be line on line, so to speak, with the helical spiral profile of the scroll plate. This will obviously never work and cause the jaws to get jammed in the scroll plate. So, we go to the rectangular profile that is 7.5 by 2.5 millimeters for the scroll plate and increase it. Modify the existing sketch by converting this rectangle to construction lines and manually draw an offset rectangle that is slightly larger than the scroll plate rectangle. Add a dimension between the existing rectangle with the amount of 1/4 millimeters. We can now see that there is some clearance between the helical spiral profile of the jaws and the scroll plate along a radial axis from the center of the three jaw chuck outward. However, we note that there is no clearance between the jaws and the scroll plate from the top side. Let's go ahead and modify the sketch to change that as well. We first need to change the end of part by dragging in the feature tree. Then, edit existing sketch and remove the coincident constraint and then add a new dimension of 0.5 millimeter. Here, I note that there is a small amount of wall for the jaw. Remember that we are 3D printing this part. 3D printed parts may snap easily depending on factors such as geometry, layer direction with respect to applied load, and quality of layer adhesion, etc. I will feel more comfortable by changing this wall thickness to something more reasonable for a 3D printed part. Let's go ahead and change it to 3.5 millimeters. We are done with the three-jaw chuck assembly as far as creating parts and assembling them is concerned. It is always good to use Solidworks to prove to yourself that the assembly is correct and will function properly. Otherwise, you will be running a lot of extra prints, resulting in wasted time and filament. Of course, this is still better than walking onto the shop floor and giving your subpar design to a machinist who instantly finds basic flaws in it within seconds. But, still nevertheless, this is a bit of a heartache. For the case of this assembly, we want to see some proof that the combine feature for the three jaws resulted in the proper cut profile on the bottom. We will check this by placing jaw 1 in an arbitrary location that it can achieve while the helical spiral profiles mate with one another. Now, we need to create a reference axis to use for measurement purposes. We create this axis by first creating a plane in the middle of the part and then creating an axis where these two planes intersect. Then, we measure the distance between the center axis and this jaw. Then, we place one of the other jaws at this exact distance because that is what we want from our 3-jaw chuck. Then, we must ensure that the helical spirals for the other jaw and the scroll plate are meshing properly at that distance. This measured distance turns out to be 47.54 millimeters. Now we create a plane that is parallel to the midplane of jaw 2. This plane is required in order to set a distance mate between the jaw 2 midplane and the newly created plane. This distance is set to 47.54 millimeters. We now need another assembly plane that is perpendicular to the previously created assembly plane to view the cross-section of the jaw and odwalla. Everything looks great. Thanks for watching this video. I appreciate any likes and subscribes as this video took a bit of time to make. Also, feel free to leave me a comment regarding the video or even another video you would like to see.